Watch this packet. It leaves a browser, passes through a corporate firewall, through a proxy, through a load balancer. At every step, something inspects it. It looks like an ordinary HTTP request, and every piece of infrastructure on this diagram thinks it is. The server sends back a response, status code 101, switching protocols. And from this moment on, that connection is no longer HTTP. It's a WebSocket, a completely different protocol running over a TCP connection that every firewall and proxy along the path still believes is an HTTP connection. A WebSocket is an HTTP request that stops being HTTP. It's a lie told to the infrastructure between your browser and your server. When you look at WebSockets this way, few other things start making more sense. Why they need special server support, why load balancers get weird around them, why reconnection is on you, and why sometimes you just shouldn't use them. We're going to look at 3 ways to move data between a browser and a server: HTTP, server-sent events, and WebSockets. HTTP works by a simple rule. The client asks a question, the server gives an answer. The exchange ends, and then everyone forgets it happened. The server doesn't remember you. It doesn't call you back. It responds, and then it's done. That simple rule comes with 4 promises baked into it. 1, stateless. The server remembers nothing between requests. 2, short-lived. Connections exist just long enough to answer and then close. 3, client-initiated. The server never speaks first. And 4, infrastructure-friendly. Every firewall, proxy, CDN, and load balancer on the internet is built around the first 3. HTTP's design is what makes the modern web cheap. You can put 50 servers behind a load balancer, and it doesn't matter which one gets your request. You can cache responses at the edge. A request can pass through a dozen pieces of infrastructure, and none of them need to understand your application. They only need to understand HTTP, which is the same everywhere. These 4 promises are why HTTP runs on everything. But a lot of what we want to build in a browser, notifications, live prices, progress bars, needs the server to say something the client didn't ask for. Promise number 3 gets in the way. The obvious workaround is to have the client keep asking. Polling. Every 2 seconds, a fresh request. Most come back empty. It works, and it keeps all 4 HTTP promises intact, but you're paying for a full round trip for every check, and your users wait up to 2 seconds for any update. So 2 different protocols were designed to get around this. One bent HTTP's rules, the other broke them. We'll do the honest one first. Seeing what you get from bending the rules is how you know when breaking them is worth it. Server-sent events is built on a single observation. Of those 4 promises, you can bend one short-lived without breaking any of the others. Do that, and you get real-time server push almost for free. The client makes a normal HTTP GET request. The server accepts it, but instead of sending a response and closing, it keeps the connection open and writes events down to the client as they happen. The response body just never ends. That's the entire protocol. No upgrade step, no new connection type. From the infrastructure's perspective, it's a regular HTTP response that happens to be very, very long. And the other 3 promises are intact. The client still initiated the request. The connection still goes through every proxy and firewall that speaks HTTP. The server can be any backend in the fleet. Nothing about SSE requires routing a specific client to a specific server. The server code is about as simple as it gets. Set the content type, write events into the response, clean up when the client disconnects. And the client side is built into every browser. Event source. No library. When the connection drops, the browser automatically reconnects. You don't write that code. It's part of the protocol. And it sends the last event ID it received so the server can pick up exactly where it left off. Server-to-client streaming. Automatic reconnection. Event IDs. Built-in browser API, no library, no special server. It's been in Chrome, Firefox, and Safari since 2010, but Internet Explorer never supported it, and Edge only joined in 2020, which is probably why the industry skipped it through the 2010s when IE support still mattered. And think about what most real-time features actually are. Notifications, live dashboards, log streaming, progress updates, all one direction. The server has something to say, the client listens. That's SSE's entire sweet spot. There's one practical limitation. EventSource, the browser API, doesn't support custom request headers, so you can't attach an authorization bearer token the usual way. You authenticate through cookies or a token in the URL. If you really need custom headers, there's a fetch-based polyfill at Microsoft/fetch EventSource that adds them back in, but using it means re-implementing the browser's retry logic yourself. It's the main reason teams bail on SSE and reach for WebSockets, but it's a constraint on auth-flow, not on what real-time features you can build. So 3 promises fully intact. 1, gently bent. No new infrastructure. If that's enough for your feature, you're done. But if both sides need to talk, you have to break a promise, not just bend one. For a chat, a multiplayer game, a collaborative editor, anything where both sides send messages independently, we need to break 3 of the 4 promises at once. The connection has to be long-lived. The server has to remember you, and the server has to speak first. 3 promises gone, and yet we still want the 4th one. We still want this thing to travel through the infrastructure of the internet.
But there's a catch. Invent a new protocol on a new port with persistent bidirectional connections and firewalls block it, proxies get confused, corporate networks reject it. The internet was built for HTTP's 4 promises. So WebSockets don't ask, they smuggle. They disguise themselves as an HTTP request, pass through every piece of infrastructure that thinks it knows what HTTP looks like, and only after they're safely on the other side do they drop the disguise. 3 steps. That's the whole trick. Step 1. The client sends what looks, to everything that inspects it, like a perfectly ordinary HTTP GET request. Any firewall that understands HTTP understands this. Any proxy forwards it along without blinking. Tucked inside it is a polite request to the server, upgrade WebSocket. Translation, if you also speak WebSockets, I'd like to stop speaking HTTP after this. If the server doesn't know about WebSockets, it ignores the header and the request is just a normal HTTP request. It breaks nothing. And the client sends a random base64 value, a challenge. Step 2, the server responds, also from the infrastructure's point of view, with a perfectly normal HTTP response, status 101, switching protocols. A code that's been in the HTTP spec since the 90s, designed to let protocols do exactly this. The server sends back its own base64 value. The server takes the client's key, appends a fixed string, a specific GUID defined in the WebSocket RFC, SHA-1 hashes the combined value, base64 encodes the result, and that's what it sends back. This isn't encryption, both values are public. The magic GUID is written right in the RFC, anyone can look it up. As security, it would be laughable. So what's it for? It's a password only WebSocket-aware servers can produce, and it defends against 2 things going wrong. First, a client sends upgrade WebSocket to some ancient or misconfigured server, maybe a dumb proxy that just echoes headers it doesn't recognize. Without the challenge, the client can't tell a real WebSocket server from a pretender that happens to copy headers around. With the challenge, only the real one can produce the right answer. Second, some caching layer, a CDN, an HTTP proxy, could grab a valid handshake response and serve it to a different client later. The challenge blocks that too. Each client generates a fresh random key, so only a live server talking to that client right now can compute the matching answer. A cache response from yesterday won't match today's key. So the magic GUID isn't security, it's proof that the thing on the other end knows what WebSockets are and is answering this client's handshake right now, not echoing headers, not replaying yesterday's cache. For a protocol designed to travel through infrastructure it doesn't trust, that's the minimum sanity check. Step 3. The moment the 101 response finishes sending, both sides stop speaking HTTP.
The TCP connection is still open. The firewalls and proxies along the way still see an open connection they already approved, but what's flowing across it is now an entirely different protocol. A compact binary framing protocol built for low overhead. Text frames, binary frames, continuation frames for long messages, plus ping, pong, and close. None of it looks like HTTP. None of it would survive on its own, but because it's flowing through a connection that began as HTTP, it gets where it needs to go. That's why WebSockets work on ports 80 and 443, the same ports every HTTP connection uses. There's no WebSocket port. It couldn't be. The whole point is to travel on trusted infrastructure. So that's a WebSocket. A real-time, bidirectional, persistent protocol delivered through the plumbing of a one-way, short-lived request-response web. The handshake is the disguise. The 101 is the moment the disguise comes off. It's a clever design, but every deception has a cost, and the cost is that the infrastructure catches on. The handshake worked, the connection is up, both sides are sending frames, but every piece of software between the browser and the server, the web server, the load balancer, the NAT gateway, the corporate proxy, was designed around HTTP's 4 promises. 3 of those promises are no longer being kept. Start with the web server. A traditional HTTP server has a pool of worker threads. A request comes in, a thread handles it, sends the response, and the thread returns to the pool. Each thread is busy for milliseconds at a time. That's the reason HTTP servers handle huge traffic with small thread pools. The workers cycle fast. Picture it as a restaurant. Waiters take an order, bring the food, move on. Each waiter serves 20 tables a shift. It works because each interaction is short. Now put a WebSocket connection on each table. Every customer who sits down gets a dedicated waiter who stays at their table until they leave, whether or not anyone's talking. For 1,000 customers, you need 1,000 waiters. For 10,000, 10,000. The restaurant's economics fall apart, not because customers are more demanding, but because the waiters never come back to the pool. Same thing on a real server. Each thread carries stack memory, roughly a megabyte. With short HTTP requests, fine, threads cycle before memory adds up. With WebSocket connections, threads are pinned for hours. At 10,000 concurrent connections, you're managing 10 gigabytes of thread stacks. That's not a WebSocket problem, it's the HTTP server model breaking because one of its core assumptions, that requests are short, is no longer true. The fix is to throw out the thread per connection model. Instead, a handful of threads sit in an event loop, reacting only when a connection has activity. 1,000 idle connections cost almost nothing. This is why WebSockets feel native in some environments and awkward in others. Node's event loop, Go's Go routines, Java's virtual threads, each lets you hold thousands of connections cheaply. When a framework claims WebSocket support, what that really means is our concurrency model doesn't assume the short-lived promise anymore. HTTP's statelessness is what makes load balancers easy. Any request can go to any backend. If one dies, the next request just goes somewhere else. A WebSocket, once the handshake completes, is anchored. The TCP connection lives on exactly one backend, and whatever state that backend holds for the client lives there with it, nowhere else. You don't technically need sticky sessions for the first connection. The load balancer could route the handshake anywhere, but that connection will drop, and the client will reconnect, in production, constantly. When that happens, you want the reconnection landing on a backend that already remembers who the client is. That's what sticky sessions do. And if any backend needs to send a message to a client connected elsewhere, you need a shared message bus. Redis PubSub's the common pick, because the backend with the message isn't necessarily the one holding the connection. And none of this is really about WebSockets. It's every layer of infrastructure designed around HTTP's promises having to be rebuilt or worked around once those promises stop being true. The server's concurrency model, the load balancer's routing, each one is the infrastructure catching on when a new set of promises emerge. There's one more piece of infrastructure to notice. NAT gateways and routers sit between billions of home networks and the internet, keeping tables of active TCP connections. Because HTTP connections are short-lived, those tables stay small and cheap. To keep them that way, most NAT gateways silently evict connections that have been idle for a few minutes. Cellular carriers are more aggressive, some evict in as little as 30 seconds. So an idle WebSocket gets quietly killed by your user's own routers, and you don't find out until the first frame fails to send. The fix is heartbeats, ping and pong control frames sent every 30 seconds to stay under the shortest NAT timeouts. Every production WebSocket server runs this loop. Ping every 30 seconds. If a client doesn't pong back, terminate the connection. Thanks to silent NAT and eviction, that's the only way you'll ever know it's gone. Heartbeats keep idle connections alive. They don't save you from the connection actually breaking. When an HTTP request fails, you've got layers of infrastructure catching the failure. CDN caches serve stale content, load balancer health checks remove dead backends, application code retries with backoff. Worst case, the user hits refresh, and because an HTTP request is stateless and repeatable, running it again just works. Nothing was lost. When a WebSocket drops, almost none of that activates. Stateless infrastructure can't retry a stateful connection. A CDN can't cache a bidirectional channel. A load balancer can reroute the next connection, but whatever state both sides were keeping is gone. The browser won't rebuild it for you. You have to. Networks drop. Servers restart during deploys. Users close laptops, go through tunnels, switch from Wi-Fi to cellular. WebSocket disconnects in production aren't rare, they're routine. Consider this situation. A team runs a service with a few thousand WebSocket clients. They deploy normally, rolling restart, 90 seconds between old and new. The new version comes up and immediately falls over. They roll back. Deploy again the next week, same thing. The deploy itself wasn't the problem. Every client that got disconnected during the restart reconnected the instant the service came back. 2,000 clients trying to reestablish in the same half-second window. The reconnection storm was several times larger than the service's normal peak traffic. It's called a thundering herd, and it's a WebSocket-specific problem. HTTP never had simultaneous long-lived connections to drop in the first place. 3 ideas to fix this, and production WebSockets does all 3. Exponential backoff. After each failed attempt, the delay doubles. A client that can't reconnect isn't hammering the server every second. Jitter. A small random addition to each delay, so thousands of clients who all failed at the same moment don't all hit the same doubled interval in perfect lockstep. And reset on success. The moment a connection is established, the delay resets. Otherwise, a brief reconnect followed by another failure would start the next retry at 30 seconds, which is terrible UX and also happens to mask bugs. 3 ideas, maybe 40 lines of code, and every WebSocket project eventually writes a version of it. And remember, SSE gave you this for free. Automatic reconnection with a server configurable retry interval built into the browser. Because SSE only bent one promise, the browser could keep doing its normal retry behavior. WebSockets broke too many. The browser can reopen the connection, but it has no way to rebuild the state both sides were keeping, so it doesn't try. Web evolves under a constraint. The existing infrastructure can't be upgraded. There's too much of it, and most of it isn't owned by anyone who could. Network engineers have a word for this: ossification. The protocols at the bottom of the stack are frozen because everything built on top assumes they never change. The same pattern, not just smuggling, but working around ossification, run through every major protocol shift in modern networking. HTTP2 runs many streams over a single TCP connection, partly because network middle boxes, the proxies, routers, and firewalls along the path, had locked in HTTP1's one connection per request model. Quick was built on UDP specifically because TCP had become unmodifiable. Those same middle boxes inspect and rewrite TCP headers in ways that break any change to the protocol. None of this is accidental. It's what happens when protocols have to evolve on top of something that can't change. Every protocol you use is a negotiation between what you want to do and what the infrastructure will allow. WebSockets are what that negotiation looks like when you want bidirectional, real-time, persistent connections on a web never designed for any of the 3. If any part of this is worth going deeper on, the WebSocket frame format, scaling with Redis PubSub, or the Web Transport API, leave a comment.